Hi students, I'll try in this educational video to technologically introduce the steel beam resistance under the ultimate limit state criterion associated to the lateral torsional buckling, of course as simply and as clearly as possible. Okay, let's go. Well, the lateral torsional buckling (LTB) occurs when the steel beam is clamped at its root and subjected to dead weight at its extremity, as it is depicted by the figure that you see now in this slide. And these two real pictures depict some lateral torsional buckling occurring in steel beams. Now, based on the Eurocode 3 standards associated to the European Standards 1993, the ultimate limit state criterion associated to the lateral torsional buckling is expressed as MED, which is the design moment, divided by MBRD, which is the design buckling resistance moment, is lower than 1. This means that the design moment should not exceed the design buckling resistance moment. Well, the design moment MED is associated to the maximum bending moment applied on the beam, which is determined based on the bending moment diagram as it is depicted by the table that you see now in this slide. And as you can notice, the bending moment diagram depends on the load case applied on the beam, and there are other tables indicating more complicated load cases. Now for the design buckling resistance moment, MBRD is determined based on the formula that you see now in this slide. The section modulus WY is determined based on the cross-section class as I explained in a previous video. The steel yield stress is determined based on the steel grade and the thickness as I explained also in a previous video. The steel yield stress is denoted by Fy. It remains the reduction factor chi LT, which is determined based on the formula that you see now in this slide. As you can notice, the reduction factor chi LT can be determined in general case associated to all cross sections based on the first formula, and also it can be determined in special case associated to Rayleigh cross sections of standard dimensions based on the second formula. And also, as you can see, we have to determine first phi LT and lambda LT in order to determine finally the reduction factor chi LT. Well, phi LT is determined in general case or special case based on the appropriate formula that you see now in this slide. Of course, LT here refers to lateral torsion. And as you can see, in order to determine phi LT, we have to determine first the imperfection factor alpha LT and lambda LT. The imperfection factor alpha LT is determined depending on the buckling curve A, B, C, or D. And this buckling curve is determined in general case based on the table that you see now in this slide. And here for the limits column, H refers to the height of the cross section and B refers to the width of the cross section. And also in special case, we can determine the buckling curve based on the table that you see now in this slide. Also for the limits column, H refers to the height of the cross section and B refers to the width of the cross section. For lambda LT, it's determined based on the formula that you see now in this slide. Of course, WY is the section modulus and Fy is the steel yield stress. And MCR is determined based on the formula that you see now in this slide. And here all the components of this formula are summarized by these two tables that you see now in the bottom of this slide. The coefficients C1 and C2 are determined based on the table that you see now in the top right of this slide, depending on the loading and support conditions. And it's to note here that the coefficient C1 is determined in another way for end moment loading associated to member with end moments based on the table that you see now in the bottom right of this slide. That's all for this educational video. Please, if you have any remarks or suggestions or questions, please mention it in the comments. Thank you very much for your attention.